Now, in here, we got a fascinating article from NASA that focuses on how scientists go through the process of detecting various blips that are across the universe, and all this comes down to is all the telescopes that are actually scattered around. According to this article, 150. I can't believe that we have that much telescopes that are out there, and some of them can be really huge, like James Webb Telescope, which we're going to talk about very soon, but some of them could be very small, and these small ones are the really instrumental ones that actually helps to not only detect these particular types of blips. And when we talk about blips, there are various instances according to this article here on what causes a blip, and this blip, how this results to scientists getting all this information, looking at the collaboration with various telescopes and giving us a rich and comprehensive picture of what this blip is all about, where, location, when, and why this blip actually happened. And so let's dive into the details about this article here from NASA. Now, according to this article, it paints a picture on how the messaging works here, and it states that Stefan Lesage's phone started vibrating just after halftime on October 9th of 2022 while he was watching a soccer game in Atlanta with a friend. Now, when Lesage saw the incoming message, the match no longer seemed important, as this here is a rare cosmic event that was alerted on his phone, and he needed to get to his computer immediately to see what actually this is all about. Now, this result of this cosmic event here, which is really rare, combines two results here, one coming from the NASA's Fermi Gamma Ray satellite and that of the Neil Harris Swift Observatory, that spotted an unusually bright signal in space and sent automatic alerts to scientists all around. Now, this scientist team here, which is in this game Fermi's channel lit up with messages, as scientists coordinated their follow-up strategy. Now, what it is in this case, based on this unusual event, is actually a cosmic burst, and this may have been a brightest at the X-ray and gamma ray energies since civilization began, which is really like huge when you think about that scale of it. And these astronomers dubbed it the boat, and the boat here is called the brightest of all time. It's like the greatest of all time, GOAT. Now, there are about 150 telescopes in space and on Earth that followed up to get more details on the events. That includes NASA's IXPE, and next is using the Hubble Space Telescope, and next is James Webb Telescope, as well as the European Space Agency's XMM Neutron Telescope. And so all this here actually shows the big picture of what this cosmic event is all about. The boat is an example of what astronomers call a time domain and multi-messenger astronomy. Now we're going to look in details about what the first part means, which in this case, according to this article, it says that the time domain is actually partly referred to as the events that happens in the universe that telescopes can observe as they unfold, such as supernova or the merger of two neutron stars. However, when we look at the multi-messenger astronomy, this here refers to the variety of messengers that deliver information from the universe, including all forms of light, high energy particles, and ripples in space-time, which are called the gravitational waves. Now, this article further gives us a contrast between how the universe tends to actually show that broad change, which actually really tends to be slow, like for example here over 1 million to billion years, but compared to just how these celestial bodies actually perform their specific events. Like for example, according to this particular article here, it says that this actually lasts between, let's just say, days to, let's say, fraction of seconds. And so having all these instruments being able to detect these bright lights or sound waves or all those particular scenarios is really fascinating and sophisticated here. And this here can include many outcomes in terms of these celestial centers. So these celestial centers can include central black holes that eat material, or we have black holes that actually suck plasma from nearby stars. We have stars maybe exploding, or we have neutron stars colliding with black holes, which is pretty cool to see, hopefully. And we have neutron stars that collide with neutron stars as well. We also have black holes merging with other black holes, and this is really incredible to see how powerful all these observatories and telescopes are able to detect these forms of outcomes here using different types of avenue how this particular information are sent. So pretty interesting here. Now looking at this scenario here, which focuses on gamma rays, there are two watchdogs that NASA actually uses here that focuses mainly on a wide field range of this particular resource here, and this here includes the Fermier and the Swift. Now if you look at the details of what the Fermier involves here, the Fermier instrument here is the Fermier's gamma ray burst monitor alongside its large area telescope, and the second one, which is the Swift, means that it is called the Swift's burst alert telescope. And so these instruments are really key here when it comes to anything that has to do with, hey, is there's a burst that's actually out there or collisions that comes up here, those are involved in that trigger that alerts the systems of all these scientists to be able to look really deep into where this here is coming from and possibly how this was actually and why this event happened. So now when this alert system kicks in here, we have various scientists that actually come together and most importantly collaborate on various telescopes here, bringing those results together from other telescopes and their points of view in order for we to get a rich result here that addresses the following: the when, the where, the why, all these events actually, and also what really happened here that results in that blip that is generated from that particular collaboration of those two instruments that are the watchdogs. And so here, according to this particular article here, it says here that by specifically looking at the boat, which is the brightest of all time that was generated here, it says that using numerous telescopes, scientists determined that this here, which is the unusual bright burst, actually came from a supernova, which is specifically a core collapse of a massive star rotating rapidly. And this here later, with the data from NASA's Neutron mission, scientists found that the jet of material that shooting out from the exploding star had a more complicated shape that they originally thought. Now this boat here lasted for around 600 seconds, and there is a new one that actually happened 5 months later, and this one here actually is, according to this article, happened on March 2023, and the assigned signal is called the GRB 230307A, and this here lasted for around 200 seconds and showing the same characteristic or similar in terms of that bright blip that is generated here. And so this here, due to the infrared data from NASA's James Webb Telescope here, scientists determined that this new second bright signal here may have had a very different origin, and this origin here is assigned to be, according to this article, the measure of two neutron stars that is about 1 billion light years away from Earth. And this here is what NASA detected also as an element created here, which is really a rare element, and this element is called tellurium. And this is suggesting that this neutron star merger created this heavy element, and it's really fascinating to dive more into this particular process that led to this heavy element creation here. So now this result is definitely puzzling according to some analysts here, and there are many more things to actually dive into to know more about it. Like for example, the merging neutron stars shouldn't produce such long gamma ray bursts, and the current models of atomic physics do not entirely explain the mid-infrared wavelength that Webb detected, and this person hopes that Webb will help us learn more about these kinds of events in the next few years. Now, according to this particular first segment of the boat, which is a time domain astronomy, this lets us to get fundamental answers on the properties of the universe, of fundamental physics itself, and the origins of elements. So this is really according to Burns in this particular article here. So looking at a multitude of messengers here, which is the other segment of the boat, this here is associated with fleeting cosmic blips that also help scientists reconstruct the origins. Now, the initial 2015 discovery of the gravitational wave of LIGO, the Laser Interferometer Gravitational Wave Observatory, showed that the universe could be observed in a brand new way and begin a new era of possibilities for using multiple messengers to study sudden blips in the universe. Now, in 2017, scientists demonstrated that potential by combining gravitational wave observations with data from many different ground and space-based telescopes and observatories to study a kilonova, now, or we call it a neutron star merger, that in this case is called GW170817. Now, among the insights from the extensive study of this kilonova, Burnin and colleagues used it to make the first precise measurement of the speed of gravity. That's pretty interesting. It's around between 0.8 to 1.2 times the speed of light. So it could be really close to the speed of light, 0.8 to actually pass the speed of light. That is really incredible to see that particular speed. And this here, according to this part here, says which would be fully consistent with the theoretical prediction of general relativity that the speed of gravity is exactly the same as the speed of light. Pretty awesome. And this here is the last major confirmation of a prediction from Albert Einstein. According to this illustration, it shows a domed neutron star whirling towards their demise in this illustration. Now, in here, this proves that gravitational wave bleeds away orbital energy that is causing the stars to move closer together and merge. As they collide, some of the debris bursts away in particle jets moving at nearly the speed of light, producing a brief burst of gamma rays. That is what is detected by those two watchdogs by NASA. And here is another final animation here that captures a phenomenon observed over the course of 9 days following the neutron star merger known as the GW170817, detected on August 17, 2017. This includes a gravitational wave, which is shown as the pale arc that you see right here, and this here also shows a near light speed jet that produced gamma rays, which is shown as the magenta moving outward here, and here it also shows expanding debris from a kilonova that produced ultraviolet, which is what we see here as the violet right here. Now, This here also shows optical and infrared, which are the blue, white to red emissions, and once the jet directed towards us expanded into our view from Earth, the X-rays, which is colored blue in this simulation right over here. So overall, I hope you found this really informative in terms of the detection of various blips in the universe and how scientists collaboration with all the incredible instruments, and most especially detection of gamma rays through those two watchdogs, helps to shape our understanding and hopefully the future of this particular experiment or exploration of the universe here, based on behaviors of black holes, neutron stars within or among themselves, or celestial beings in there. Hope you found this really informative. Let's know your thoughts about this in the comment section down below. By that way, you can talk to us soon. Stay smart as always and believe in yourselves.